Yeah, I'm very pleased to be sharing this this result today. This is joint work with Pascal Golin, Kenichi Kawarabayashi, Ojong Kwon, and Zhang Elong. All right, so first off, I'm going to talk about heading sets. So if we have a family of graphs F, then a heading set for the family in a graph G is a subset of the vertices of G such that when you delete these vertices, then you no longer have any subgraph in the family F. So as an example, if F is the family of cycles, then a heading set for the cycles in a graph is what's sometimes called a feedback vertex set. It's a set of vertices such that when you delete it, what's left is a forest. Now, one somewhat straightforward observation to make is that if a graph has many disjoint cycles, then every heading set for these cycles must be large. You must have at least one vertex for each of the disjoint cycles. But a question you might wonder is whether the reverse is also true. So if you know that every heading set is large, can you somehow find many disjoint cycles? And this is the well-known theorem of Erdos and Pósa. For every graph G and every positive integer k, the graph either contains k disjoint cycles or a heading set of size of the order of k log k. So in general, we say that a family F has the Erdős-Pósa property if there's some function which relates these two quantities. If there's some function such that every graph either contains k disjoint copies of subgraphs in F, or there is a small heading set of size, at most, some function of k. All right, so here's an example of where such a property does not hold. If instead of considering all cycles, we only consider cycles of odd length, then instead, Lovas and Schreiber observed that for every k, there is a graph which doesn't even have two disjoint odd cycles. However, the smallest heading set for the odd cycles in this graph will have size at most k. And the construction is what's known as an Escher wall. So in an Escher wall, it's something like this graph here. So we start with a wall, and then we add in some edges which connect the top row to the bottom row. But we do it in such a way that all of these edges are going to cross each other. So the one that goes from the top left will go to the bottom right, and the one from the bottom left will go to the top right, and so on. And we can do this so that if you just look at the wall itself, all of the cycles that are contained just in this planar part are even cycles. So there's no odd cycles there. However, if you set it up carefully, you can make it that each of these crossed edges will give you at least one new odd cycle. And then you can sort of see that you won't be able to find a small heading set for the odd cycles. So if you just delete a small set of vertices, you're still going to be able to connect across one of these diagonals and then finish it off into an odd cycle. However, it's slightly less easy to show, but still true, is that all of the odd cycles in this graph intersect each other. Okay, so when we looked at cycles, we saw that the only reason, in some sense, that the heading set should be large is because there's many disjoint cycles in a graph. But when we look at odd cycles, this is no longer true. We need some other, there must be some other obstruction to having a small heading set for odd cycles. So a half integral packing of cycles is a collection of cycles such that no vertex is used by more than two of them. So if you look at 3 cycles in this packing, they won't have a common intersection. And observe still that if we have a large half integral packing, then there can be no small hitting set, because every vertex in your hitting set will cover at most two things in the packing. So what Reed was able to show is that if we look at this half integral packing version, then we do get some sort of analog of the Erdős-Pósa theorem. So there is a function such that for every k, every graph either contains a half integral packing of k odd cycles, or a small vertex set, so size at most f of k, hitting all odd cycles. Okay. So there have been several results since here that generalize this one. And I'm going to talk about just one of them because it is a nice general theorem which encompasses a lot of the other results. So, but first I need to describe what are called oriented group labellings. So, an oriented group labelling of a graph assigns every edge a weight from some group as well as an orientation. And then if we consider a walk in this graph, then we take the weight of the walk to be the sum of the weights of the edges, but some of them will get a -1 coefficient if they're traversed backwards. So what does this mean? So if I draw a cycle like this, but maybe some of the edges are pointing the wrong way, and then say the weights are like 1, 2, 3, 0, then I can consider the walk that goes around this cycle. So consider this walk here. And then the weight will be 1 plus 2, and then -3 because this edge is pointing the wrong way, and -0 because this edge is pointing the wrong way. And in general, if you look at a walk corresponding to a cycle, the total weight of this walk might depend on where you start the walk, and it might depend on what direction you're going. But if this equals 0, which in this case it does, then the cycle has 0 weight regardless of where you start this walk. So this is really independent. It's just a property of the cycle itself. Okay. So now given an oriented group labeling of a graph, we can start to describe classes of cycles. So for example, cycles of 0 weight or cycles of non-zero weight. And if we imagine that the group is Z2 and every edge has weight 1, then the odd cycles are precisely the cycles of non-zero weight. Okay, so this is a quite broad generalization of the result of Bruce Reed. So there is some function with the following property. If there is a graph with 2 oriented group labellings, this is with arbitrary groups, if we consider the set of cycles which are non-zero with respect to both of these labellings, then for every integer k, we either have a half integral packing of k cycles from O, or a hitting set for these cycles of size at most f of k. Okay, so this is quite a remarkable result because the function f doesn't depend on the group. So these can be really arbitrary groups. They don't have to be abelian or anything. But the question that Hyun, Yosun, Wallen asked in this paper was whether this result could be extended to more than 2 labellings. And the result I want to talk about today is not going to answer this question completely, but it is sort of going to give some partial answers to this question and also give some new results. So first, let's talk about non-oriented labellings. So, and particularly we're going to focus on abelian groups for the remainder of the talk. So if we have an abelian group, then a labelling with this group is just going to assign a value to every edge. So we don't have an orientation anymore. And now we just take the weight of the cycle to be the sum of the weights of the edges in the cycle. And of course, the order doesn't matter because we're in an abelian group. So if we have multiple labellings, we'll say that the cycle is nowhere zero if it's non-zero with respect to each labelling. And sometimes we will, if we have multiple labellings, we'll just consider it to be a single labelling with the product group instead of a bunch of separate labellings. Okay, so this is our result. So for every pair of positive integers, m and omega, there is a function with the following property. So if you have abelian groups for each I from 1 to m, and subsets of these abelian groups, and you have a graph, then consider the set of cycles whose value in each of these labellings avoids the subset omega I. Then for this class of cycles, we have this half-integral Erdős-Pósa property. So provided the subsets that are avoided, these subsets omega I, are all bounded, then we are guaranteed to either find a half-integral packing of k cycles from this class of cycles O, or a hitting set for O of size at most, this function fm omega of k. Okay, so there's a lot going on in this theorem. One nice consequence is that for groups which only contain elements of order 2, there's no difference between the oriented labellings and our unoriented labellings. So in this case, we are actually able to resolve the question of Kuhn, Jus, and Wallen. Because the important thing that our result does is it allows us to go from more than 2 labellings from 2 labellings to more than 2 labellings. But there's a few benefits from what we are able to do, and there's maybe a couple of disadvantages. So we don't have this result for oriented labellings, and we don't have this result for non-abelian groups. But instead of just considering the non-zero cycles, we can specify this more complicated thing of cycles avoiding a particular set, omega I. So if we just considered omega I to be 0, then there would just be the nowhere zero cycles. Okay, so I'll talk about a couple of examples of what this theorem is able to show. So if we have a graph G, and we have some collection of subsets, S1 to Sm, then either we have a half-integral packing of k cycles, each intersecting all of the sets Si, or we have a hitting set for these cycles of size at most f, m, 1 of k. And to show this, we just consider the group labeling with the integers such that the set that we're avoiding, this omega I, is just 0 for all I. And we take the weight of an edge to be 1 if and only if the edge is incident to some vertex in Si. Now, in order to find a cycle of non-zero weight, nowhere zero weight with respect to these group labelings, it would need to contain some edge incident to each of the sets Si. But if a cycle contains an edge incident to Si, it will also contain a vertex in Si. Oh, sorry, yes. So this is it's just some function that we find in this theorem here. So I said we have this f omega m omega. So when m is m and omega is 1, then we get this corollary here. Okay. So here's another consequence. So given any pair of positive integers s and t, there is either a half integral packing of k cycles of length s mod t, or a hitting set for these cycles of size f. Now the function is now f sub 1 comma t minus 1 with k. So here we only need one group labeling, which we take to be a labeling with the cyclic group zt, but we take the set of forbidden values to be almost everything in the set, everything except the value s. So this omega 1 will be a set of size t minus 1. And we just give every edge the weight 1. And now a cycle will have weight s if and only if it has length congruent to s mod t. Okay. So are there any questions at this point?
Can you explicitly describe the function
No. Well, we never explicitly define it in the paper. You could derive it, but it's some very large function that's very complicated and messy. We never made any effort to optimize this, for example. It would be, yeah, I have no real idea what the order of this function is, but it's very big. Even, yeah, I mean, I don't know what the optimal function would be. I don't have any good lower bounds, but yeah, we certainly made no effort to optimize this function. And the functions that you could compute from our proofs are going to be very, very large.
Do you mean that you have some methods to find the function?
Yes, there is some. Yeah, you could. Yeah, in our theorem, it's not. You could derive some explicit function from our proof. It's just it's not something that's going to be worth writing down. But yeah.
What is the value rate for?
Sorry.
In the theorem.
Oh, I don't know off the top of my head. Do you know, Samuel? No. Yeah. I think that's something else. Yeah, I don't know for Reed's theorem, and I don't know if since Reed's theorem someone else has come along and tried to optimize that. So there might be some reasonable bounds for that case. But yes, so this result is really just the existence of some finite values. That's I won't be going into like any precise bounds in this talk. Okay. Right. So here is a very, very rough sketch of the approach that we take to prove this result. So I'll just quickly go through the setup. So we have some abelian groups, gamma 1 to gamma m. And for simplicity, let's just assume that all the forbidden sets omega I are just the set containing 0. So we really are just considering nowhere 0 cycles for the purpose of this talk. Okay, so what we want to do is by proceeding by induction on k, we want to show that there is some integer fm omega of k such that every graph labeled with all of these abelian groups will have a half integral packing of k cycles from the set O or a small hitting set. Okay, and to sort of help us out, we will start off by assuming that the smallest hitting set for some particular graph that we're considering is very much larger than fm omega of k minus 1, which is some value that we will presumably have by induction. And using this fact, we want to try and construct a half-integral packing of k cycles in O within the graph G. So in order to start this inductive proof, I should point out that if we just consider fm omega of 1, then we just are looking for a half-integral packing of 1 cycle from O. So either we will find some cycle from O, in which case we have a half-integral packing of size 1, or we can take a hitting set to be empty. So we can start the inductive proof at least. I hope that's clear. Okay, so the first thing that we want to do in order to prove this result is to find a subwall within the graph G. And particularly, we want to find a subwall which cannot be separated from any of the cycles in O by any small set. So by a wall, what's this graph drawn on the slide is an elementary wall. So this is just a planar graph. You can think of it as a hex grid. But in general, we consider any subdivision of this graph to also be a wall. But if we take a subdivision of this graph, then for technical reasons, we record which vertices are subdivision vertices and which vertices are the original vertices of the graph. So the original vertices we call the nails of the wall, and most of them will have degree 3, so they're easy to identify. But there will also be these nails around the outside which have degree 2, and we just record these for technical reasons. Okay. So the basic strategy is going to be this. So using the wall, we want to break apart cycles from the set O into subparts, and then we want to reroute these subparts through the wall and stitch them back together to form new cycles, which hopefully are nowhere zero. And the advantage of doing this is that hopefully by rerouting through the wall, we can control how the intersections happen between the cycles. Okay, that's a very broad overview of the sort of thing we want to do. But before we can get started, how do we find a wall within the graph? So the tool that allows us to find a subwall within a graph is what's known as a tangle. So very loosely speaking, a tangle of order k is simply a way of selecting a small side of every small order separation. So for every separation of order at most k, we select some set A out of the two sides of the separation. And we do it so that no 3 of these A sets will cover the entire graph. Okay. So how do we do this in our case? So let's consider some minimal hitting set for the set of cycles O in the graph G. And consider a separation AB, which has order at most size of t divided by 6, for example, and such that A contains at most as many of the vertices of T as B does. So somehow the set T is going to determine which side of the separation we're considering to be the small side of the separation. Okay. So the first thing to note is that if we consider the set T set minus B union the intersection of A and B, this set has size strictly smaller than T. So maybe I'll draw something for this. Okay, so we have some graph G. We have some separation AB. And maybe we have, say, T1, T2, T3 equal to the intersection with A, B, and A intersect B. So, okay, so if we consider the set T set minus B union A intersect B, so this is this set here plus this set here, then because the size of T1 is smaller than the size of T3, this can be at most half of the vertices of T. And then we know that the size of the separation is T divided by 6. So this set plus this set is certainly smaller than the set T. So by our choice of T, this means that this blue set here is not a hitting set for the cycles in O. Okay, so that means that after we delete the blue set, there must be some cycle left over, and this cycle has to live inside B. So this is some cycle in O. Okay. But we can now assume that inside the set, inside the set, the graph G induced on A, we can assume that the number of the largest half integral packing of cycles from O will have size at most k minus 2. Because if there was a half integral packing of k minus 1, of size k minus 1, then we could combine the half integral packing over here with this cycle here to get a half integral packing of k cycles from O. And that's everything that we're looking for. Okay, so, but given that G minus A has no half integral packing of size k minus 1, then we can apply induction to say that there should be a heating set for this of size, heating set T prime of size at most the previous value of this function fm omega. So let's draw this function here, T prime. Okay. But now we can form a new hitting set by combining T prime with the entire separation and also this set T3, so just the intersection of T and B. Okay, but since this is guaranteed to be a hitting set, we know that since we chose T to be minimal, we can actually deduce that the number of, okay, I think this should be, this is wrong here, this should be an A. Yeah, so what we know is that the intersection of A with T, so the size of this set T1, has to be of size at most fm omega of k minus 1 plus T divided by 6. And since we're assuming that T is very much larger than, that's a mistake as well. So this should be very much larger than fm omega of k minus 1. What we actually find is that almost all of the vertices of T are on the large side of the separation. So in particular, you can't, it's not possible to combine 3 of the smaller sides of the separation to cover the graph. So we really find a tangle of this order. Okay, and this is useful because, as many of you may know, if a graph has a large tangle, then it contains a large subwall. And it's not just that it contains a subwall, it really is this wall that we're looking for, where it's sort of connected to all the cycles in some way. It's connected to all the cycles from O. Okay, so step 1 more or less complete. We can find at least a wall within the graph, And that's the first step towards proving this result. Okay, maybe, yeah, so I mentioned that the purpose of finding the wall was so that we could reroute cycles through the wall to change where they intersect, something like this. But if we want to reroute, if we want to take cycles and reroute them through the wall, then it would be nice if we could do this without changing the weight of the cycles that we construct. Otherwise, things are going to get very messy. And for this reason, what would be nice is if we could find a wall where all of the edges of this wall have 0 weight. So that would be kind of the ideal situation. And unfortunately, that's a little bit too difficult. So what we do instead is the following. So we apply this algorithm here. So we consider the group labellings gamma 1 to gamma m. And we're going to start with all of these labellings being unmarked. And if we can find a large subwall, which is gamma I bipartite, for some unmarked gamma I, I should say, so bipartite just means that every cycle has weight 0 with respect to this labelling. So if we can find a large gamma I bipartite subwall, then we restrict to this subwall. We mark the coordinates that we've satisfied, and we update our criteria for what we consider to be large, and then we just repeat. So we keep on going until we get to a situation where, for all of the labellings where we're not bipartite, we don't have any large bipartite subwall. So what does it mean if we don't have any large bipartite subwall? So for every unmarked labelling, there will be, in every large subwall, some non-zero cycle. Any questions? Okay, so now this gives us a wall where let's imagine imagine for the moment that we've just found a wall and all of the labellings are bipartite now on this wall. So all of the cycles in this wall have 0 weight. So what we can do, so we can apply what's called a shifting operation. So for any vertex of a gamma labeled graph and any element from the group of order 2, if we add the element g to the weight of all the edges around a vertex, so we pick some vertex, and maybe that starts with weights 1, 2, 3, and we're working in Z6. Then what we can do is we can add some element of order 2 to the weight of all of the neighboring edges. And this operation won't change the value of any cycle in the graph because every cycle will intersect these edges in either 0 positions or 2 positions. And the element that we're adding has order 2. Okay, so if we have a gamma bipartite free connected subgraph of a gamma labeled graph, then we can actually shift all of the edges of this graph to 0. So the graphs that we're actually considering are these walls, which are not exactly three connected graphs, but we can do something very similar, where what we can do is perform some shifting operation so that every path between vertices of degree 3 will have weight 0, which ends up being sort of enough for what we want to do. Okay. So the next lemma that the next theorem that we're going to need is this result of Wallen. So firstly, given a set of vertices S, an S path is just a path whose endpoints are in S, but which is otherwise disjoint from the set S. Okay, so what we find is that for any group labeled graph, the set of S paths for any subset S satisfies the Erdős-Pósa property. Okay, and we're able to use this result in the following way. So if we have some labeling such that every cycle in O is lambda non-zero, then since we have no small fitting set for O, there is no small hitting set for lambda non-zero nail paths. So these are S paths where we take the set S to be the nails of the wall. And roughly speaking, the reason for this is that the wall is, we can find for any cycle, we can link it to the wall, and then if, and within this linkage, we will then be able to find a lambda non-zero path if the cycle is lambda non-zero. Okay, but the upshot of this is that we get the following lemma. For example, that for each of the labellings gamma I, we can find a large set of disjoint paths which are gamma I non-zero, whose endpoints are the nails of the wall. Okay. So in theory, this could be still very messy. We could still have paths that behave very badly. So we could have paths like this all over the place. But for simplicity, I'm going to assume that sort of thing doesn't happen. So I'm going to assume that we're in a situation where whenever we find these paths, they really attach to the boundary of the wall. So it looks more like this. And sort of the idea of this is now we set up these paths like this, and then we can link them together through the wall to form cycles. So that's going to be the setting. But even if we assume that things are so nice for us, we still run into problems. So let's just consider the case where all of the labellings are Z2 labellings, and we just have 3 of them. Well, what we might find is something like this. So here we have this wall in black, and if we look at these labellings on the left, these 3 red paths are each non-zero in the first coordinate, and these labellings on the right are each non-zero in the second coordinate, and the labellings on the right are also non-zero in the third coordinate. So for every coordinate, we can find a set of disjoint paths which are non-zero. However, this gamma-labelled graph, if we assume that all the black edges have 0 weight, doesn't actually contain any nowhere zero cycle. Because if we take an odd number of things from the left and an odd number of things from the right, then the third coordinate of the sum is going to be 0. But if we take an even number of things from the left, then the first coordinate will be 0, and if we take an even number of things from the right, then the second coordinate will be 0. Okay, so this is sort of a problem for our approach at the moment. So to get around this, what we do is we consider a new group labeling with a quotient group. So if we consider the group, the subgroup of this product group, which is generated by these two elements, 1, 0, 1 and 0, 1, 1, then what we see is that there's no element of this subgroup which is nowhere 0. That's sort of exactly what we just discussed when we were trying to find this nowhere 0 cycle. But what that means is that if we consider the labeling with this quotient group, then every cycle in O must be non-zero with respect to this quotient group labeling. So what we can actually do is we can, using the same idea as before, we can find a set of disjoint paths which are non-zero with respect to this quotient group. In other words, we can find a set of disjoint paths whose values are not inside the subgroup generated by these two values. Does that make sense? I see my co-authors nodding, so I'll keep going. Okay, so here is the simplified scenario that I want you to consider. So we have some wall, and we're building a collection of sets of disjoint paths with endpoints spread out across the boundary of the wall. And I want to just consider this to be as simple as possible. So let's just imagine all of these paths are disjoint from each other as well. So everything is sort of as nice as you could want it to be. So at every step, we can select any subgroup of the product group which doesn't contain a nowhere 0 element. And with respect to this subgroup, we can find a new set of paths whose values do not lie in the subgroup. So in particular, this allows us to, for example, ask for a set of paths which are non-zero with respect to the labeling gamma 1, because we can quotient by the subgroup whose values all have 0 in the first coordinate. But we can do more complicated things. So if we get stuck, as in this thing from this example here, if we get stuck in a situation like this, then we can look at the quotient group with respect to the subgroup that we're sort of stuck in, and then proceed. And the goal is, of course, to find some collection of paths which we can string together to form something whose weight is nowhere 0. Okay. So the key lemma that allows us to do this is the following. So I'm now just going to consider the group theory question. So if we just have a family of elements of some product group, I want to find some subfamily whose sum is nowhere 0, for example. Okay, so here's the setup. If we have a collection of families, each of size m plus 1, and in the ith family, all of the members of the ith family differ in the ith coordinate. Okay, so in this setting, my claim is that we can select some representative from each family such that the sum of these representatives will be nowhere 0. Okay. So how do we do this? So here's the idea. So what we're going to do is we're going to select the representatives independently at random. And we're going to consider the sum of the representatives that we select. Now, if we fix the values of the first m-1 choices, then the probability that the final choice, the choice of the final representative is selected, so that the sum of all of the representatives is 0 in the mth coordinate, is at most 1 divided by m plus 1. This is because all of the members of the family Fn differ in the mth coordinate. And there's only one possible way that we could select this last value so that the sum is 0 in this last coordinate. But by symmetry, now, the probability that there is any coordinate, which is 0, is at most m times 1 divided by m plus 1. So in other words, in other words, there is some positive probability that when we do this random selection, we will find really a set of representatives whose sum is nowhere 0. Okay. And so I won't go into precisely the details, but that's basically how we end up getting this process to terminate. We can use this idea to resolve this problem. Okay. So what about all of those unmarked coordinates? So remember, we at the start we split the labellings into two sets, some of which we were able to shift to 0 on the wall, more or less, and some of which we could not do that. Some of them we instead had some other condition. So what do we do with the remaining coordinates? Because when we reroute through the wall, we sort of have no control at the moment of what the value will be in these coordinates. So what I want you to imagine is that we are somehow able to construct a half-integral packing of cycles which are non-zero with respect to all of the marked coordinates. So that's the first step is to do that, which I've very, very roughly sketched how you might approach it. So what we want to do is that once we have this half-integral packing, we want to set aside some collection of large subwalls for every cycle in the packing and every unmarked labeling. Okay? So, and then recall that the property that the unmarked labellings have is that inside every large subwall, we at least are guaranteed to find a non-zero cycle for that labelling. And what we can actually do is, using only the edges of the wall, we can reroute the cycle that we've constructed through the gamma I non-zero cycle in such a way that the gamma I value will change. And note that the values of the marked coordinates won't change because we just reroute through the wall where all of the marked coordinates have 0 value. Okay. And if we choose the cycles carefully, what we're actually able to do is randomly select which of the possible reroutings we actually use. And we can use a similar argument to the one that we used before to obtain a cycle which is now nowhere 0 with positive probability. So this allows us to update our half-integral packing to a half-integral packing of nowhere 0 cycles, which, if everything works out the way that I'm claiming it will complete the proof. Okay. Yeah, any questions at this point? This is probably a good time to ask for questions. Okay, so I want to finish just with a couple of questions. So the first question, simply put, is can we extend our result to from cycles to S parts? So formally, is there a function with the following property? So again, we imagine that we have a graph labeled with a set of M abelian group labellings, and still we have a forbidden set omega I for each labelling. But now instead of the cycles, we want to also fix a vertex set and just consider the paths whose endpoints are in this set and which are otherwise disjoint from this vertex set. But the question is whether we get the same conclusion that in this setting, the half-integral Erdős-Pósa property should also hold. One last question I want to ask is a slight extension on the question asked by Kuhn, Jus, and Wallen. So we're not even able to answer the question of Kuhn, Jus, and Wallen, so this is somewhat ambitious. But so what they asked was whether with multiple oriented group labellings, we could have a half-integral Erdős-Pósa property for nowhere zero cycles. But what if we instead ask for something similar to what we were able to do in the non-oriented setting? So instead of just nowhere zero, can we actually forbid some set omega I of bounded size? And then, now we need to be a bit careful because I mentioned that the weight of a cycle will have zero weight irrespective of where you start the walk and which direction you go. Well, this won't be true anymore. If we care about the actual value that the cycle takes when it's non-zero, then we don't have this symmetry property for arbitrary groups. So here we just consider simple closed walks essentially, and ask whether these have the half-integral Erdős-Pósa property. Okay, thank you.
Thank you. Any questions?
Is there any simple formula for f and omega when given m and omega have some special type?
Oh, is there any? You want to know if there's any case where we do know what the value should be? I don't know of any. As I say, I don't even know for the case of odd cycles what the function should be. I guess if omega is the empty set, then you could use the Erdős-Pósa theorem. So that would be order k log k. But that's the only one I know. Yeah, well, yeah. So there are other results that do some of the. So some of the corollaries I mentioned, for example, the S intersecting sets. So this one here. So when m equals 2, this was already known. So the case of m equals 2 is already shown by this result. Where we can use an oriented group labeling in much the same way as we use the non-oriented labeling. And in that case, maybe there is some better function, or maybe there is some explicit function somewhere. Yeah, and there's a few other results like this. But I don't know any of the explicit bounds that people have computed. I think a lot of the time, at least the initial papers that you see, are just looking for the existence of the function and often won't explicitly calculate it. But yeah, I guess that is an interesting question though, of like, can you put any reasonable bounds on these functions now that we know that they exist? We have some lemma about a Lobel bound, which basically just says that we use it to show that the function really does depend on m and omega. But it's sort of a very crude lower bound. It's yeah, we don't have much in the way of we really have. Oh yeah, no, the function is independent of the graphs, and yeah, it doesn't depend on the number of vertices of the graph. Yeah, right. So it is. This function. It really is just a function from integers to integers. And yeah, the size of the hitting set is really just some bounded integer. It's not some proportion of the vertices.
So Unjong asks, is the main statement algorithmic? It is not even clear to me whether how fast one can detect a non-zero walk from one vertex to another.
Oh, is our main statement algorithmic? Because we apply so many of these other results, I don't know, because I don't know which of these other results are algorithmic. But I would guess that it probably is, that you could get some algorithm from our.
I would guess the same.
Yeah, certainly there are several black boxes which we appeal to. For example, this theorem of Wallen that I mentioned somewhere. Yeah, and yeah. But I would guess that there should be an algorithm based on our proof. Oh no, actually, wait. Not based on our proof, because we do this argument that we make about cleaning the wall. I mean, I presented it as an algorithm, but this is not an algorithm really. It's like, I mean, if there's a large subwall, restrict to that subwall. That's, I mean, it's in some sense it's an algorithm, but not in. This isn't a reasonable algorithm really. And yeah, this argument we really do appeal to in the proof. Maybe if you're careful, you can sort of get around it, and yeah, there may still be some way to do it. But I think, yeah, this is probably the most problematic step in terms of finding any reasonable sort of algorithm.
Right, and Tony asks, do you really need to use randomness? We didn't need to in the oriented case.
It's the way, that's the way I like to think about that argument, but it's a simple counting argument. The randomness is, it's a uniform random variable taken over a finite set. Of course, we could just count all the possible outcomes and do it some other way. Yeah, this is the way that to me, that's the most intuitive way to think about it, but it's absolutely not essential to the proof. Yeah.
Okay. Is there any more questions?
At the moment, yeah.
I could mention where it is that the proof breaks down. If you look at oriented group labellings instead of group labellings. So the problem with oriented group labellings is that if you have, let's say, suppose that we have these two paths and we want to connect them into the cycle. Well, if we use this path in this direction, then we're sort of forced to use this path in this direction. Which means that we can't just add these two weights together in the oriented case. We're going to run into trouble whereas in the non-oriented case, we don't care about the direction that we traverse these edges, these paths, and everything works nicely for us. So just very roughly speaking, that's the reason that we moved away from the oriented group labellings. I just remembered it because Tony asked.
Right. Any other questions? If not, let's